Okay. So one task done. Second task is I have to share my screen. Okay, so I today will solve to 3 small exercises on some decidable or undecidable problems about context-free grammars. Um, Maybe I just again highlight one thing. What are the things about context-free grammars that are already known to be solvable? So you know that emptiness is solvable, membership is solvable, okay, things like that. And for that we have used the pumping lemma, right? On the other hand, if we consider a grammar and ask the question whether the grammar can generate everything over its alphabet of terminal symbols, we have proved that this cannot be decided in general. Okay, so that was an undecidability proof that uses the valid computation history method. Okay, so let us see maybe a couple of other examples that we cannot solve in general. So the first question today is this. Let G be a context-free grammar. Okay, it's provided in some encoded form to a Turing machine. And the Turing machine wants to decide whether that language of that grammar is closed under concatenation. This problem is undecidable. So how do you approach? No suggestions? Maybe I start with the reduction that we have seen in the fullness proof. From the complement of the halting problem, we have generated a grammar okay, so the input was M and some string. From that I generated a grammar G such that the language of G is the complement of the set of valid computation histories of M on X. Okay. And we have encoded a valid computation history of M on X by a sequence of configurations separated by some separator like hash. Right. And what we have done, we have proved that the complement of this language, valcomp M, X, is a context-free language. Okay. So I am not going to the construction again today, but you say that if M does not halt on X, what does it imply? So let us call this language L. If M does not halt on X, then there cannot be any finite valid computation history. Okay. The computation history is called valid if it ends in a halting configuration, that is in the state R or T, T or R. Okay, the machine never goes there. Therefore, what is L?
A delta star.
Delta star, right? Because there are no, this valcomp M, X is empty. Its complement is entire thing. And if M halts on X, then definitely there are valid computation histories. In fact, there are infinitely many valid computation histories, because when the machine enters the reject or accept state, it will continue to stay there. Maybe always moving right and things like that. Okay. So once it enters T, for example, you can have next configuration, which is also in T, next configuration, which is also in T, and so on. In particular, this valcomp M, X is non-empty. And therefore, its complement is not equal to delta star. Therefore, if I can solve this problem, whether the language of a grammar is the entire delta star or not, then I can also solve the complement of the halting problem. But I know that this is not solvable. This is not decidable. This is not even semi-decidable. This will prove that this problem is not decidable or not even semi-decidable. Okay. So now we ask you a question. This reduction suffices to settle this question as well. Can you say why? Okay, so for this exercise, the same reduction works. Why?
So because if M does not halt on X, then L is delta star, and delta star satisfies the property that it is closed under concatenation.
Exactly. So in this case, we have delta star is equal to delta star concatenation delta star. So this property is satisfied. And then you have to say that if M does halt on X, then this is not satisfied. Whatever your L is, it is not closed under complementation. Not complementation, what is that? Concatenation. So how do you show that? Okay, if M does halt on X, then there is at least one valid computation history, configuration 0, configuration 1, configuration 2, and so on, up to some number of steps, n maybe. Okay, so this is followed by hash. So if M halts on X, so this is a valid computation history. So this is not in the language, because L is the complement of this. So L will not contain this. Right. So if I now break this in two parts, this part up to C0 and starting from hash, ending somewhere here. So I have a hash C0, hash C1, hash C2, and so on up to Cn hash. Now what can you say about hash C0 and this second string? Are they in L?
Yes, sir.
They are in L?
Yes, sir.
They are in L because this is in L because this is the format is not valid.
Yes.
It should end in
Hash.
hash, but hash C0 is not ending in hash. And why is this
So
not in?
because the start state should begin with C0 or C0.
Yeah, so C1 is not the start configuration. No, the state in C1 may be the same as C0, but
Sorry, sir.
the head position is not the leftmost one. Because every transaction, every transition is of the form, if you see the left end marker, you move forward. Okay. So this is in L This is in L, so this is not the start configuration. Because of the head position. Okay. But if you concatenate these two, you get a valid computation history, and therefore this is not in L. This says that this language L is in this case not closed under concatenation. Happy? Okay. So now let me ask a different question. So here you see that I am specifying the configurations one after another, C0, C1, C2, up to some point of time. Now what I will do, I will specify C0 as it is, but I will reverse C1 and then specify C2 as it is, then I will reverse C3 and so on. Okay. So this alternately, I am keeping the original configuration and reversing it. Okay. Original, reverse, original, reverse, original, reverse, and so on. Okay. And this way I can generate several strings. Okay. If C0, C1, C2, blah, 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 this is a valid computation history. So I alternately keep the string or its reverse. Okay. This is, let us call valcom, valid computation history, written in this alternating manner. Okay. M1W or M1X, whatever. Okay. So you have seen the complement of valcomp itself is context free, and now I say that the complement of this is also context free. Can you give me a reason why? So have you seen the recording? I do not.
Excuse me, sir.
Yeah, tell.
Sir, we can use the same method of reduction which was used for proving that valcomp complement was context free.
Yeah, it's basically the same proof.
Yes.
In fact, that valcom thing is slightly more complicated. Okay. So something is not in this language if either it is not syntactically correct or it is not consistent with the transitions of the input Turing machine M. These are the two possibilities. Now, syntax checking is perfect. I mean, it's basically the work of a DFA. You do not even require a PDA. Okay. And for the original Valcom thing, what we did, an NPDA somehow guessed that there is some inconsistency in some CI. And the next one, CI plus 1. Okay. So here is a hash. There are certain things there. Here is another hash, possibly followed by something. So it remembered 3 symbols at some guessed location of inconsistency. It goes here and confirms this inconsistency. 3 locations are sufficient. Okay, it may be this location or whatever. So remembering these 3 symbols in the finite control and then going to the corresponding location and finding that this does not follow from this suffices. Okay. This is, as I mentioned, quite similar to producing inconsistency in the complement of this language. Okay, complement of WW. WW itself is difficult. It is not context free. But if something is not of that form, you will have a inconsistency at least at one corresponding position. Okay. But what now I am giving you things of the form WWR or WRW. Okay, if the consistency is here, it is WW reverse. If it is here, it is W reverse W. So inconsistency checking is actually even easier, right? So what is the, let's say we have this form. You have hash, you have CI here, you have hash here. You do not have CI plus 1, but it's reverse. Then you have another hash and so on. So now the corresponding position is something like this. Here, here. So 3 things. 3 things. So you start reading this and discard. And then you remember these 3 symbols, maybe in the stack itself. You do not need to remember in the finite control. And again, discard. You may use this part. You have to just make this length equal to this length. So you use your stack and then verify inconsistency using your state or using your finite control, whatever. This is easier, right? WWR or WRW, this is easier. Okay, so this is also context free in an easier way. This was also context free, but you have to remember these 3 things in the finite control. You cannot use this stack, but this is a finite amount of information which can be stored. But here an entire computation can be done in the stack. Whatever it is, you can check inconsistency and prove that this is the complement of this language is context free. Okay. But what is interesting about this is this inconsistency checking, okay, can be done even by a DPDA. Actually, there is nothing to guess here. As you keep on looking things here, 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 you can simply push things on your stack. And after you see this hash, you pop, okay, and check for consistency. So there is actually not a necessity to guess the position of inconsistency. Simply push and here pop and check consistency or inconsistency. So this is cannot be done by a DPTA. Because you have to guess this length, guess the corresponding position. But here, if you can identify this I, then this inconsistency checking can be done even by a DPTA. Agree or not? Tell. It's in the same way we are handling this WWR. Okay, but WWR itself is not deterministic because you do not know the center. But if I have a hash at the center, in order to clearly identify that this is the center of the string, then this becomes a deterministic context-free language. Agree or not?
Yes, sir.
Okay. So here the situation is very similar, little bit more complicated. Technically, little bit more complicated. Nothing more complicated than that. Little bit more complicated. Okay. So this gives us the next part, so that this language is the intersection of two deterministic context-free languages. It's not the complement. It's the original language itself. Okay, so check consistency or inconsistency, both can be done in a deterministic fashion. So, first of all, you intuitively argue, it can be proved more rigorously, you intuitively argue why this language is not context-free in general. So of course, using some form of pumping lemma, you can prove it, but intuitively why this is not context-free. So think of this language. Is this context-free? You have separators, hash, W, W reverse, and again another W. Is it context free?
No, because once we check WR, we've lost information about W.
Yeah. So that's the idea. So you can use the stack to compare this with this or this with this. But after this comparison, the stack is lost. And exactly similar thing happens here, right? You can compare this with this, but then you cannot compare this with this. But there is an interesting thing. You can compare this with this, this with this with this, and so on. So that gives you a hint for solving part B. No suggestion? Let me write it instead of writing all this thing, then comp alt E. So you can check the consistency of C0 with C1. And since this is in the reverse form, you do not have to guess anything. You can use your stack to check for the consistency between C0 and C1. And then forget about C1 and C2. You can then again use your stack in a deterministic fashion to check the consistency of C2 against C3. C1 and C2 you cannot check for the moment, but C0, C1 you can check, C2, C3 you can check, C4, C5 you can check, and so on. For all I, you can check in a deterministic fashion whether Ci is consistent with Ci plus 1. You have the separators, right? Hash, 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 hash. So there is nothing to guess here. Convinced or not that this is a deterministic context-free language?
Yes, sir.
Okay. And what should be the other language?
So for odd values of I.
Or odd values of I. Great. The same thing, odd, same thing, consistent with this for all odd I. Okay. So now you check whether this is consistent with this. Once again, this is doable because this is presented in the reverse fashion. Then whether this C3 is consistent with C4, C5 is consistent with C6, and so on. And my valcomp alt MW will be the intersection of agree or not?
Yes, sir.
Okay. So this essentially solves the next exercise. And I stop here. Prove that it is undecidable whether the intersections of two CFLs is empty. Okay, whether the grammar of a single CFL is empty or not, this can be decided. But if you are given two grammars, whether they contain or they can generate any common string, that is undecided. So from HP, you need to, okay, generate a couple of grammars such that language of G1 intersection language of G2 is equal to empty. So starting from m hash x, you have to generate G1 and G2. So what should be G1 and what should be G2? Look at this. G1 is a grammar for this language. G2 is a grammar for this language. Right. For alt even, and G2 is a grammar for odd. Okay. So now I am not taking the complement, just doing this original language itself. But the trick is I am alternately reversing the configurations. Now if m does not halt on x, what does it imply? This means there are no valid computation histories. And therefore, again, look at this. This is the intersection of this, and this is empty. Because there are no valid computation histories. So, there is no common string generated by G1 and G2, right? Or this condition holds. So there are no okay. And conversely, if M halts on X, there are valid computation histories. So this is non-empty, but this is equal to this intersection. So this is also non-empty. Okay. So similarly, if M halts on X, agree or not?
Yes, sir.
Okay. Yeah, so I think I should stop here. If SK wants to take over, she has just nine minutes. So would you like to talk about anything?
I can ask them the question. So, yeah, we can use 9 minutes as much time required. It's an informal argument, so
Yeah,
we
that's
can use
true.
the 9 minutes.
Maybe then I will stop sharing.
Okay, so if you have gone through the lecture on modern computers and their equivalence to Turing machines, there was a question right at the end where you were asked to think about how you can informally argue that a Turing machine can simulate a C program. During the lecture, you have seen how a set of assembly language instructions can be simulated by a Turing machine. So now suppose you are given a C program instead of the compiled version. Then how will you try to solve this? So we can just recall that in assembly, The computer programs, I mean, the instructions will be of this form: copy W1 to WJ, WI to WJ, add two numbers, and so on. Jump to some address, compare two numbers. So what do you have to do? You don't have to give me full details. We don't have time, but what should you do? You know how a Turing machine can simulate a compiled set of instructions. So here, what do you have to argue?
Simulate the compiler.
Correct. So if you have a C program, then suppose you can generate this sentence. So suppose you can generate something like this, then the Turing machine, then after that, the Turing machine can simulate M on this input. So what you have to think about it is how you can convert a C program, the sentences of a C program, the code in the C program, into how the compiler will compile this program. So can anybody give me one example, like a simple example, if you? So suppose the program is initializing a variable. So can you tell me what the compiler? Have you done a course on compilers?
No, ma'am.
Oh, okay.
They will do it later in third year.
Okay. Okay, so then you can keep this in mind. So basically, when you have to think about how the compiler is parsing this. When you are initializing a variable, when you are, let's say you're declaring a variable, so basically you're marking an address in the memory for this variable and so on. Then if you are storing some value, then you're going to input that value in that address place. So using the assembly language instructions, see what declaring a variable means in the assembly language. Suppose you want to declare a variable, think about what are the steps that are required for the computer to understand that this variable has to be remembered. Then you can think of what the computer has to do if you want to set a value to that variable. So you can try to argue informally about these steps. Maybe it will be clearer once you have done a course on compilers. Eddie, do you have anything else to add?
Well, this is actually a little bit difficult for them to comprehend, but essentially you have to write a compiler for Turing machines instead of your Intel machines or other architectures. It's essentially like that. Okay, so you say malloc. So you can have another tape, a tape reserved for all malloc calls. You can give any amount of space as is desired by the C program. But you have to keep track of from where to where you have given the space. Okay, something like that. Yeah, now it's a little bit difficult for them to comprehend.
Yeah.
But I believe when they study compilers, they can think of how to write a compiler for Turing machines.
So you can keep this problem in mind and then you can think about it once you have completed your compilers course. Do you have any questions on this modern computers bit? This will not be tested. So if you have any questions, you can ask. Okay, then I think we can stop.
Yeah, we can stop, but with the I would say indication that if you can do it in a computer, modern computer, if you can write a C program, And all these things can be done by a Turing machine. This is what justifies our study of Turing machines. It's a very simple model. Despite that, it is capable of doing anything that you can conceive of. And that is what is the Church-Turing thesis. Turing machines can perfectly capture the idea of computability, despite its simplicity. So that is the, I would say, underlying insight why you study things like this. Definitely, this is not a machine which is of practical importance, although I would say that after Turing proposed his machine during World War II, maybe a few years after that, British intelligence routinely broke German ciphers. They designed a machine called Bombe, B-O-M-B-E. And Turing was not the chief architect, but as far as I know, he was part of the team. So this kind of computation must have been done, and that breaking was nothing but exhaustive search. One by one, you just keep on using different keys and find out which one matches. Unfortunately, that original model of this Bombe that was destroyed after the war. But as far as I know, it is once again built, and it's in some museum. And actually, I forgot the name of the person who was the chief architect. He was actually a person related to the postal department. Okay. But it's a Turing machine-like architecture. Yeah, so we had some use, but for the moment, this is mostly for understanding the notion of computability. Yeah, so with that note, I suppose we should stop. And that form will remain open. If you develop any further queries, please let us know. We will send you emails. And next Thursday, let us have another doubt clearance session. But this is just doubt clearance. We will not solve anything. And next Friday, we'll have 2 tests. So that's it. That's the end of the course. Yeah.
Thank you, sir. Thank you, ma'am.
Thank you for joining.
Thank you.